So this is the example we ended with last time. And mainly, I wanted to talk about taking the derivative of a piecewise defined function. So forget about all the other words on the slide. Just let's start by focusing on this function right here, the piecewise defined function. So I want to take its derivative. So this happens in 2 steps, okay? So the first step is I take the derivative of each piece. So when I take the derivative of 1 plus x, the derivative of 1 plus x is 0 plus 1. And this is the important part. I copy down the inequality, but not the equality. I just write down x less than 0 here. I didn't put the equals. Now I take the derivative of the other piece, x plus cosine x. The derivative of x is 1. The derivative of cosine x is minus sine x. And so that's the derivative. And now I have to check about this part. So what do we check? There's 2 things that need to be checked. Number 1, first, we need the function to be continuous at the point 0 in this case, because differentiability implies continuity. So I can't have a derivative at 0 if the function isn't first continuous at 0. And so it's easy to check. You can check the limits, the limit from the left, the limit from the right, and the function at the point all equals 1. So we have continuity. That's the first thing. The second thing I need to check now is that the derivative from the left at 0 and the derivative from the right at 0 are the same, because the derivative is a limit, a 2-sided limit. So here, if I check, if I take the limit of the derivative as x approaches 0 from the left, the limit is 1. And if I take the limit of the derivative as x approaches 0 from the right, so I'm going to plug in a 0 right here for the x. So you get 1 minus sine of 0. Sine of 0 is 0. So from the left, the derivative is also equal to 1. So if they're equal from the left and the right, then I can put in the equal symbol right here. And so in this problem, I didn't just copy down the less than or equal to. There's a lot more happening than just that, right? I'm checking continuity first. First, we need continuity at the point of the original function. So I need at 0, the function is defined, the limit from the left, limit from the right are defined equal to that function value. And then we need the derivative from the left and the right to be defined, to be a finite number and to be equal. So here's another example. And in this case, it doesn't work out. So I want to do an example where it works and where it doesn't. So again, I want the derivative of this piecewise defined function. Away from 0, I'm not worried about this function. So, away from 0, less than 0, it's a polynomial, no problem. Greater than 0, it's a trig function, no problem. I'm worried about what's happening at 0, when x equals 0. So now I need to check 2 things. First, I need to check continuity. So here, you can check clearly away from 0, it's continuous. And at 0, you can check the limits from the left, right, and the function value. Everything is equal to 1. So we have continuity. And now I want to take the derivative. So I'm going to take the derivative of each piece. The derivative of 1 plus x, as you know, is 1. The derivative of cosine of x, as you know, is negative sine x. But now if I check the derivative from the left and the right, the derivative from the left is 1. The derivative from the right is 0. If I plug in 0, I get minus sine of 0. The derivative from the right is 0. They're not equal. That's why I don't have an equal symbol here. You should compare why in one case I have the equal symbol and the other case I don't. Okay, so in this case, the continuity is okay, but the derivative doesn't exist at the point. Remember that continuity is the first thing that we need to check. If the function's not continuous at the point, it doesn't matter if the derivative from the left and the right are equal, because differentiability implies continuity. So we first, even for differentiability to be even possible, we first need continuity. Here we have continuity, but the derivative from the left and right don't exist at 0. So you should think about how you take the derivative of a piecewise defined function, and specifically when we copy down the equal symbol here and when we don't. Okay, so there's a little bit of theory involved there. It's not too complicated, but there's a little bit of theory. That ends my discussion on product rule and quotient rule. So let me now switch over very quickly to the chain rule, which is, I'm going to say, probably the most important derivative rule in Calc 1. So this is something we really need to, get down rock solid. So I'm going to start with an example. So if you're looking at the slides that I emailed to you on Tuesday, you will not have this first slide because I added this slide yesterday. And I've uploaded these latest set of slides to Canvas in the module. So if you want the absolute latest set of slides, if you go to Canvas, go to the lecture module for my lectures, the lecture there has this slide. So for chain rule, let me explain why I added this slide. I didn't show you the proof of chain rule. You'll see, I'm just going to give you the formula. So I first wanted to do this example to motivate the chain rule formula. So here in this example, what we want to do is find the derivative of a composition. So here I'm going to take I'm going to take f of x equal to x squared specifically, and then some function g of x that's differentiable. When I say it's differentiable, what I mean is its derivative exists for all values of x. And so I'd like to use the limit definition of the derivative to find the derivative of the composition, f composed of g, which by definition is f of g, and in this case looks like g of x squared. What I want to show you is that this formula comes up that we will later call the chain rule. So I'm trying to motivate the chain rule formula to show you it doesn't just appear out of the blue. So I'm going to use the limit definition on the function g of x squared. And you remember the limit definition says, take the function evaluated at x plus h minus the function evaluated at x divided by h, and then send h to 0. So I'm just doing the standard definition. And here, if you plug in the h, we get 0 over 0. So here I need to try some algebraic tricks. So what I noticed is we have a difference of squares. I think of this as a squared minus b squared. So I factor this as a minus b times a plus b. And now if you try to apply the limit again, you'll still get 0 over 0. So now I'm going to use one more trick here. I'm going to break up the fraction. I'm going to factor the fraction. So be very careful. This is a multiplication. All I've done is this property where if I have something like a times b over c, then I can write this as a over c times b. So that's all I've done here. This is my a over c part times, this is the part I'm calling b, if you wish. So how does this help? Well, now we use trickery. This is exactly the difference quotient that defines the derivative of g when we send h to 0. And we are sending h to 0. So this fraction here, gx plus h minus gx over h, as x goes to 0, this thing converges to g prime of x. And for the second term, if we send this h to 0, you get g of x plus g of x. Here I have 2g of x. So this is what I have written down here when I apply the limit. As I said, the difference quotient here, g of x plus h minus g of x over h, as h goes to 0, becomes the derivative g prime of x here. And the other term becomes 2g of x. So this is the derivative, but this was not the point of this problem. So we know the derivative of gx squared is 2g of x times g prime of x. The point of this problem here is I want to write this in terms of f. I want to write this derivative answer that we just got in terms of the function f. I want to bring f into it somehow. So with the function f of x, if you look, f of x is 2x squared. So f prime of x, sorry, f of x is x squared. So f prime of x is 2x. And so I noticed that we can actually write the derivative. So the derivative of the composition, f composed of g, which in this case is the derivative of g of x squared, which we showed is 2g of x times g prime of x. This part, 2g of x, that looks just like this 2x, except if we need to replace the x here, instead of having an x in here, if I replace this x with a g of x, then that looks exactly like this term. If we replace x with g of x. So 2g of x, I can actually write as f prime of g of x. So this expression here, 2g of x, if you look at the derivative, you know, we notice, oh, well, I can actually, if I just replace that x with g of x, that's exactly 2g of x. So we end up writing the formula this way. F prime of g of x times g prime of x, that's the derivative of the composition. So I wrote it again. And now this is the whole reason I did this example, because this formula is a famous formula. That formula is called the chain rule. And, you know, that's the formula we want to learn. And the chain rule, as I said here, you know, it's for the derivative of the composition. So if you try this exact same experiment with, so here I use g of x squared, where the outer function was f of x squared. If you try this same experiment with the positive square root of g of x, where the outer function is the positive square root function, or if you try it with 1 over g of x, where the outer function is the reciprocal function, 1 over x, we keep getting, if you do the limit definition and rewrite, we keep getting this formula, f prime of g of x times g prime of x. So this is not a random formula, and of course it can be proven rigorously, and I'm not going to go into the proof, but I wanted to do that example to motivate the formula, just to show you it's not coming out of nowhere. So here's officially the chain rule. So if we have two differentiable functions, so these are two functions whose derivatives make sense, and we want to find the derivative of the composition, the chain rule says the derivative of f composed of g, which is the same as the derivative of f of g of x, is equal to f prime of g of x times g prime of x. So let me just mention the language. So here, when we look at this expression, the composition here, f composed of g, we think of the function g as the function on the inside. G of x is a so-called inside function. So g of x is the inside function, and then f of x is, you know, you can see this function on the outside. So the way we pronounce f prime of g of x, we refer to that as the derivative of the outside function evaluated at the inside function. So the derivative of outside is f prime, evaluated at the inside is the g of x that's on the inside, times the derivative of the inside function. So that's typically how we talk about chain rule. It's the derivative of the outside evaluated the inside times the derivative of the inside. That's how we say it in words. So just some comments about the term chain. You know, here, because of continuity, if you follow the journey of the variable x, x gets put into the function g of x, then g of x gets put into f. Now here, because g and f are continuous, because they're differentiable, there's this chain. You know, any change or perturbation in the input variable x will be passed along to g of x because of continuity. And then any change in g of x will be passed along to f of g, again, because of continuity. So there's this like a chain reaction, or they're linked like a chain. If you shake x, that motion gets transferred to g through the continuity, and the motion in g gets transferred to f of g, you know. So that's kind of the chain idea. And the chain rule lets us track the chain of events. So if x changes a little, then g prime of x, that records how sensitive g is to any changes in x. And then the change in x will cause a change in g. So f prime here of g of x, that records how sensitive f is to any change in g. You know, so you have this chain of events that's being tracked by the chain rule at every step. And one thing you should notice here is here we have the composition of two functions. G is on the inside, f is on the outside, and we have two derivatives. There'll be as many derivatives as there are composed functions. So if I had f composed with g composed with h, I do f prime times g of h times g prime of h times h prime. You kind of, what we call peel the onion. Here we think of f of g of x kind of like an onion with layers. And I start with the outmost layer. I peel the f by taking its derivative. Take its derivative and evaluate the function at the inside. So once you've taken its derivative, you can forget about f. So now that I've taken the derivative of f, basically I pretend like it disappears. And then I move on to the next layer of the onion. I take the derivative of g times the derivative of the inside. The inside here for g is just x, and the derivative of x is just 1. You know, you can think that you're always doing chain rule. When I take the derivative of a function f of x, it's f prime of x, that's the derivative of the outside, times the derivative of x is just 1. So in a way, we're always doing chain rule. So now, you know, we have to practice. So this first example, I'm going to be very explicit, and I don't expect you to write as much as I am going to write for this first example. Okay, I'll show you exactly what I would expect from you. So here, it says find d by dx of the function y equal to 4 minus 3x to the 9th. What I want you to notice is, number one, this is a derivative problem, not a limit problem, not an integration problem. Number two, we're trying to find the derivative of a function. And when you look at 4 minus 3x to the n, I want you to think that's a composition. So here we took the being raised to the 9th power, we took that function and we put 4 minus 3x inside that function. And that's the kind of composition I want you to think of this as, where the outside function is blah raised to the 9th power, and the inside function is 4 minus 3x. So as I said, I was a little very explicit with this problem. So here I'm going to explicitly define what the outside function looks like, blah raised to the 9th power. The inside function is 4 minus 3x. Then I say I'm trying to find the derivative of this composition. And according to the chain rule, it's f prime of g of x times g prime of x. Now, let me go in and calculate what does f prime of g of x look like? And let me calculate and see exactly what does g prime of x look like, and let me put those pieces together. For f prime of g of x, we're first, for f prime of g of x, first find f prime and then plug in the g of x. So here, I first find f prime, which is 9x to the 8th. And then right here for this x value, I'm going to replace it with 4 minus 3x. So f prime of g of x, which is f prime of 4 minus 3x, is going to look like 9 times 4 minus 3x raised to the 8th. So this part and this part, I replaced it. F prime of g of x. And g prime was very easy. G of x is 4 minus 3x. So g prime, so here, g of x is 4 minus 3x. So g prime is just the constant -3, which I've multiplied right here. So as far as the derivative goes, this is the derivative. But we have one final step where we want to simplify it, combine any like terms. And here, 9 times -3 is -27. So this is the chain rule in all its glory. I don't expect you to put in all these steps that I put in. What I expect, the work I'm expecting to see from the students is this stuff here that I'm going to put in a red box here. So let me show you. Basically, this is what I'm expecting to see from a student. So starting out, trying to find the derivative here, right? So trying to find the derivative, want you to realize this is a composition. This is a composition, so let me use the chain rule. Let me do derivative of the outside evaluated at the inside. You're looking at this and saying the outside function is basically blah raised to the 9th. Never mind about blah. I'm just doing blah raised to the 9th, variable raised to the 9th. How do you take that derivative? Bring down the 9, copy down the blah, subtract 1 from the exponent. So there I have 9 blah to the 8th. That's the derivative of the outside. And then once we're done with the derivative of the outside, basically I can now ignore the outside function once I've done the derivative of the outside. And then I have to do the derivative of the inside. Derivative of the inside is right here, -3, and then simplify. So just what's in here in the red box is the work I would expect to see from a student. I was obviously being very explicit in this example because, I'm trying to teach it. And when I'm trying to teach it, I'm not trying to hide any of the steps or make it confusing, hopefully. So the next example, so here's what I'm going to do. The examples are going to get more and more complicated, and I'm going to skip more and more steps, okay? So this next example, slightly more complicated. I want you to notice it's a derivative problem, step 1, but the other thing I really want you to notice is here, we're trying to find the derivative of a product. X times sine of x to the 9th. So first of all, that's a product. And then the sine of x to the 9th, that's a composition. So I want you to see this as x times, and I put big parentheses, put the 9 out here, and write in a sine of x. This is really what it looks like to us. We see explicitly there's a product and there's a composition. So starting out, I'm first going to do a product rule because it's a product first. And so here's my product. So I do derivative of the first times the second function. Here the first function is just x. So derivative of x is just 1. Now I'm going to put in a plus. I'm going to copy the first function. And then I want to do a chain rule on sine of x raised to the 9th. So think of this as blah raised to the 9th. So the derivative of the outside, I'm going to do a power rule. Bring the 9 down in front, subtract 1, and then I'll have to do the derivative of the inside. So here I have plus x, and this part is my derivative of blah raised to the 9th. Where I'm ignoring what's on the inside. You bring down the 9, subtract 1 from the exponent, just copy down. Times, so that was the derivative of the outside. Now I have to do the derivative of the inside, which is just the sine of x part. That's the inside function. And I've memorized the derivative of sine of x is cosine. So we take all this junk off, take a look at it again. Let's go slow. So first, it's a product rule. So here, derivative of the first times the second plus, I copy down the first function, which is just an x. Now for the derivative of this function, I see a composition. I do derivative of the outside, which is you bring the 9 down and subtract 1. That's the derivative of the outside. And then I got to do derivative of the inside, which is cosine. So you should take a look at that, you know, and kind of let your eyeballs get used to what you're seeing and work through it slowly. It's a little weird. That's the derivative. The only other thing left to do is to simplify it. When I multiply stuff together, I notice that there's a common term, sine 8th to the x, sine of 9th to the x, so I can factor out a common term. That's what I do here. I factor out the sine of, you know, sine to the 8th, and that's it. That's my final answer here. So, you know, there's a couple of parts to this. We recognize it's a derivative. We recognize there's a product rule involved. And in doing the product rule, we recognize there's a chain rule in there, you know, and this is kind of the way it's going to work. We're going to have multiple things happening at the same time. So as I said, I'm making these problems harder and harder. So here's another derivative problem. And what I hope you notice right away is that we're trying to take the derivative of a quotient. And I hope right away you're saying the first thing I'm going to try here, because it's a derivative problem and because we're looking at a quotient, is to use the quotient rule. So I've got my quotient here that I'm taking the derivative of. I've memorized my quotient rule. The way I like to start by squaring the denominator. So I draw the big fraction bar and I square the denominator. So now the way the numerator works is we're going to do derivative of the numerator times this original denominator down here. So the derivative of secant, I don't know if you remember, the derivative of secant is secant tan. So here I have secant tan times the denominator, which is 1 plus 2x to the 1/2. And so now the way quotient rule works is we're going to do minus, copy down the original numerator, so it'll be minus secant x times the derivative of this denominator here, this original denominator. So for 1 plus 2x to the 1/2, I'm using a chain rule. So this is important now that you realize that here for 1 plus 2x to the 1/2 for the derivative. Oh, by the way, notice that I rewrote it. It's written here in the radical form, and I went from radical form to fractional form because we have a derivative rule for blah raised to a number, you know. And so here, when I'm doing the derivative, blah raised to 1/2 is the outside function. So I bring the 1/2 down. I'm going to have 1 plus 2x to the 1/2 minus 1. 1/2 minus 1 is negative 1/2. That's the derivative of the outside. I now have to do, that's the derivative of blah to the 1/2. I still need to do the derivative of the inside. The derivative of 1 plus 2x is 0 plus 2, or just 2. So that's where this expression here is the derivative of the denominator with a chain rule. That's important. You know, we're studying chain rule. This is where I've used the chain rule. And so as far as the derivative goes, that's the derivative. But we still need to simplify it. Okay, so here I just want to review a little bit of algebra. So the first thing I'm going to do is I'm going to multiply 1/2 and 2 and just get rid of those. So those won't be there at all. When I multiply those two, they'll disappear completely. So the other thing I'm looking for are common terms. So this 1/2 and this 2 are gone. The common terms I see are the following. So first, you know, 1 plus 2x is a common term, and secant of x is a common term. For the 1 plus 2x, we factor out the lowest power of the common term. So I'm going to factor out 1 plus 2x to the minus 1/2 and secant x. So that's what I'm factoring out. The 1 plus 2x to the minus 1/2 and the secant x. Remember, when you factor out, what that means is we're dividing each term by the thing we're factoring out. So here, I'm going to divide this first term here by secant x 1 plus 2x to the minus 1/2, and this second term here, I'm also going to factor out secant x 1 plus 2x to the minus 1. So here, that's what I've done here. I've written it explicitly. So here you can see we've got the first term divided by the thing we're factoring out, minus, here's the second term divided by the thing we're factoring out. And now we get some nice cancellations. So here you'll notice the secant cancels completely. And this term that's in the denominator, it's with the negative exponent. That means this should come up. So you get 1 plus 2x to the minus 1/2, it goes up. So you get 1 plus 2x to the 1/2 times 1 plus 2x to the 1/2. And so that'll just be 1 plus 2x times tangent. For the second term, everything cancels. The secant cancels. The 1 plus 2x to the minus 1/2 cancels. So this second term is just a minus 1. So when I simplify it, that's what I get. So as I mentioned, here we're expecting to see 1 plus 2x times tangent x after you simplify it. And this second term here, this is just 1, but there's a minus sign in front of it, so you get that minus 1. And then the thing I factored out is just in the front here. So one final step is I bring this negative exponent downstairs. So here you see this is a negative exponent. So I can bring it down. Multiply here, this is 1 plus 2x to the first power. So 1 plus 1/2, I get 1 plus 2x to the 3/2 in the denominator. And so after simplifying, here's my final answer. And the simplification part is really important, because if we now want to figure out where the derivative is 0 or something like that, I have to simplify it. This middle step is usually skipped. Typically, this middle step here is usually skipped. So folks will go from this step directly to this step where we factor everything out and simplify. You know, it's up to you. This is certainly would be fine with me. Of course, I would say, you know, make sure you don't do any mistakes. But if there's any ever doubts, you can do it the explicit way and really make sure you're not making any mistakes. Remember, it's okay to take a shortcut as long as you know what it is you're shortcutting. And you can go back and check it the long way if you have to, you know. But yeah, so you can include that step. As I said, most folks do not include that step. You know, typically, we just factor it out and simplify the inside and do that step in our head. But as I said, I'm a big fan of writing out all the steps. You know, that's the best way. You're never going to make a mistake, hopefully, you know, if you write out all the steps and really keep checking at every stage. So I want to do a slightly more abstract problem. Still chain rule. You know, I want you to start, your eyeballs now have to start getting math vision. We got to be able to see things through our math vision. It's kind of like smell-o-vision, but with math, okay? So here, the things I want you to notice, first of all, there's a derivative problem, not a limit problem, not an integration problem. Second of all, we're trying to find the derivative of a composition. The function on the inside is this x squared plus g of x. The function on the outside is this function f. Note that we don't know what f is, and we don't know what g is, and it doesn't matter. We're still going to find the derivative. We're not going to let that stop us, okay? But the most important thing is you notice the derivative problem and that we have a function, a composition of functions. So I'm going to do the derivative. As usual, I'm going to do derivative of the outside. The outside function is f. Since I don't know what the actual function is, the derivative of f, I'm just going to write as f prime. So derivative of the outside evaluated at the inside looks like f prime of x squared plus gx. we're peeling the onion. And here I've peeled one layer. I've peeled the outer F layer. So now I'm interested in x squared plus gx. We're taking the derivative of x squared plus gx. We've reset. This is like a new derivative problem. So I say to myself, oh, this is a sum. And so the sum of the derivative is the derivative of the sum, right? So here I can take the derivative of x squared plus the derivative of g. The derivative of x squared is 2x. The derivative of g, because I don't know what g is, I'm just going to say the derivative of g is g prime. So there's your derivative of the outside, which I underline in red, times your derivative of the inside, which is, and you should look at the original function and see the pieces. See that x squared plus g of x is inside the function f for a composition. Of course, you know how it is in math. We have to make things worse and worse and worse. So I say now find the second derivative of this weirdly defined f of x squared plus g of x, where we don't know what f and g are. So as you know from the theory, to find the second derivative, I need to take the derivative of the first derivative. So here's the first derivative that we found. And now I'm taking a derivative of that derivative. Okay, this part is a little tricky, okay? So I want you to pay attention here. First thing I want you to notice is the thing we're taking a derivative of is a product. So here's the first function is this f prime of x squared plus g of x times the second function here is 2x plus g prime of x. So what does that mean? For my first thing I'm going to do is a product rule. And for my product rule, the very first step, I need to take the derivative of this function, f prime of x squared plus gx. This is a composition. So this part now is really important. When you look at f prime of x squared plus gx, the outside function is f prime, the inside function is x squared plus g of x. So we're going to do a chain rule on the first term times the second, plus we'll copy the first term times the derivative of the second. So here is the chain rule on just the first term. Okay, so here, this first term, I've done the chain rule. So you see the outside function is f prime. So the derivative of the outside is f double prime, and then I just copy the inside. The inside function here is x squared plus g of x. So derivative of the outside times the derivative of the inside. The derivative of x squared plus gx is 2x plus g prime of x. Don't forget, I still need to multiply by this function here. Derivative of the first times the second, that's this function right here that I'm multiplying. Here's that function. So the 2x plus g prime of x and this other term, 2x plus g prime of x, I will be able to combine. So what we're looking at here is the derivative of the first function using chain rule, which is these two terms here, times the second. Plus, now I'm going to continue with my product rule. Plus, I copy down the first function. So the first function is just f prime of x squared plus g of x times the derivative of the second function. So here, I'm taking the derivative of 2x plus g prime of x. The derivative of 2x is just 2 times 1, or 2. The derivative of g prime, because I don't know g prime, what g is, the derivative of g prime is just g double prime. So that huge mess is our product rule. Here's the plus in our product rule, okay? So I want you to see the pieces. So this was derivative of the first times the second function plus the first function times the derivative of the second. So, those are all the pieces here. The stuff in the yellow boxes are derivatives. And yeah, the only final step is to do some simplifying. The only simplifying to do is to combine these two terms. 2x plus g prime of x times 2x plus g prime of x becomes 2x plus g prime of x squared. And yeah, that's the derivative there. So you should take a look at the slide again. It's a bit abstract. It's not difficult. It's just, you got to get used to the game we're playing. And the more you can mess around with it, the better it'll get. So I wanted to do essentially chain rule again, but in Leibniz notation. It's a bit of a rigmarole. It's the same thing. So here we have y is a function of u and u is a function of x. So I made a little diagram here. You can see here's y. It's a function of u. But if we look at u is a function of x. So in this indirect way, y depends on x. So it's very reasonable to ask about what's the y derivative with respect to x. Again, chain rule tracks the dependency between the variables. So here's what chain rule looks like in Leibniz notation. So I want to find dy dx. Y, however, is not a function of x, it's a function of u. So the first derivative you take is dy du. Now I don't want a du down here in the denominator. I really like a dx. So we're going to look at the derivative of the function u. The function u is a function of x. So here we do du dx. And according to the chain rule, this du down here and this du up here, they sort of cancel out. So these aren't fractions. They're not really canceling out. I think a better word is that they compensate for each other. And at the end of the day, what happens is the chain rule is able to tell us how du is affected by any change in dx. And here, this term really is just a link in the chain. It just kind of helps us to make a connection between y and x. And u is just kind of an intermediary variable that's in between. So we can also write this chain rule in this form, f prime of u times u prime of x, because y is the function f, and the derivative of f with respect to u is just f prime of u. And du dx, similarly, u is just a function g of x, which is a function of x. So the derivative of u with respect to x we can write as u prime of x. And now if you replace the u with g of x and the u prime with g prime of x, then it looks exactly like our previous chain rule. It's identical. There's nothing new here. They're just playing this kind of variable games. So here in f of u, if you replace the u with g, you get f of g. So here on the left-hand side, the derivative of y with respect to x is the same as the derivative of the composition. And our answer here, f prime of u, u prime of x, if you replace this u with g and replace the u here with g, you get back our chain rule. Derivative of the outside, evaluated the inside, times the derivative of the inside. It's just the chain rule, but in different notation. Couple of comments. dy du and du dx are not fractions, even though we've written them that way. They're actually limits, so they're derivatives, which are actually limits. But the notation, as I said, is to emphasize the links between the variables, and I'll show you here in an example. And again, it's just the usual chain rule idea that because of continuity, any change in x will be felt all the way up to y, through the continuity, through the composition. So here's an artificial problem. We're given y here is this function of u. Y is equal to u to the 5th plus 1, and u is the cotangent of x. We're asked to find dy dx. Look, y is not a function of x. Y is a function of u, but u is a function of x. So this is a reasonable question. And if you just want to do this directly, you could. If you just take this cotangent, plug it in for u, and then take the derivative and use a chain rule on the u to the 5th, that would be the way we would have done it a couple of slides ago. Okay, here we're going to do it in 2 steps. This is kind of, a little extra work to some extent. So here, using Leibniz notation, what I really want you to get is this notation. So here I'm trying to find dy dx, okay? So I start with dy, and if I look at the function y, the only derivative I can take is with respect to u, because the function y only knows that it's a function of u. It doesn't know u is a function of x. So then the du, that's my clue. So here I'm gonna now, since I got a du at the bottom, I want a dx at the bottom, let me now look what's going on with the derivative of u. So then I look at du, but du, if you look at the definition, it only knows about x. U is a function of x. So here I have to take the derivative of u with respect to x. So at the end of the day, the chain rule will now tell me that in some sense, you can think of the du's as, you know, not canceling, just the du at the bottom and the du at the top are sort of counteracting each other. And what we end up with is the derivative we're looking for, dy over dx. So now here, I'm just going to follow the recipe. I'm going to now do dy du. I'm going to take the derivative of this function here with respect to u, and then multiply, you know, take the derivative of this function here, u, with respect to x, multiply the two. I'm just going to now follow the rules. So the derivative of u to the fifth plus 1 with respect to u, and I'm going to multiply that with the derivative of cotangent of x with respect to x. U to the fifth plus 1, it's a sum, so I can just take the derivative of each term and add it. U to the fifth is a variable raised to a number, so I'm going to use the power rule. Bring the 5 down, subtract 1, the derivative of 1 is 0. So you get 5u to the fourth. I've also memorized that the derivative of cotangent is negative cosecant squared. So this is something that you basically just have to memorize. We could use a quotient rule and try and find the derivative that way, but on a test, you know, at this point, these are facts that we should know. These are facts that are known facts in this class, the derivatives of the trig functions. So the only final step here, as far as derivative is concerned, we're done. The only final step here is, because we were asked to find dy dx, it says find dy dx. This notation implies x is the independent variable. So what I want is an answer that's totally in terms of x. So this variable u here, I'm going to replace it with cotangent of x because we're given u equals cotangent of x. So my final answer looks like this. It's you know, it's just a chain rule problem, and the chain rule derivative happened right here. But it's kind of done in 2 steps. That's the derivative of the outside, and then this is the derivative of the inside. So it's just a regular chain rule problem, but it's broken up into 2 steps. So 5u to the fourth would sort of be your derivative of the outside, and minus cosecant squared is the derivative of the inside. So this is a little more random. Let me do this one and stop. And so this problem, when I see something like this, so y is a function of u is a function of w is a function of x. So in an indirect way, y is actually dependent on x, right? Y depends on u depends on w depends on x. So here we're asked for dy dx. Okay, so here's how I use the notation. So I start, this is what I'm looking for, dy dx. So I'm going to start with this function here. I'm going to start with the dy. So now if you look at how y is defined, the only derivative I can do for y is with respect to u, du. So now this du in the denominator says, okay, let me check what's going on with the u function. So I look at the u function, see it's a function of w, and take the derivative here, derivative du. The only variable that the function u knows about is the letter w because of this definition, u equals g of w. U only knows about the letter w. So here I have a dw, which is not what I'm looking for. I want to end up with a dx. So this denominator, dw, says, okay, check the derivative of the w function. So then I go dw, look at the function for w, its independent variable is x. The only derivative I can take here is dx. And now I step back and go, oh, you know what chain rule says in a roundabout way, these du's quote unquote cancel. They're not actually canceling. they're counteracting each other. And these dw's counteract each other. So at the end of the day, what I've found is dy dx, which is what I was looking for. That's kind of how I use the notation here, this Leibniz notation. And it kind of, everything makes sense, you know, just fits if you just kind of ask, okay, what's the only variable I can, you know, take the derivative here? And I like to make a variable chain. So I'll start with y and say, okay, y is a function of u, oh, but u is a function of x. And so then I can keep track of the derivatives. Oh, here I'm going to need a dy du. And then down here, I'm going to need du dx. You know, you kind of keep, oh, I need one more chain here, right? It doesn't end at x. I'm sorry, I messed up my chain. So u goes to w, and then w goes to x, right? So this goes to w, and then this goes to x. And so you can see the derivative from here to here is dy du, du dw, dw dx. Okay, so I'm going to pick it up with this example here. I'll finish up this example next time. So thank you for your time, everybody. I'm going to stop right here.